afternoon, everyone. Welcome to this MTech MARC final jury. Our students, our Phase 2 students are nearing the end of their 16-month journey at MTech. As you might know, our research employs a, let's say, scientific approach, and as you will see from the dissertations, they are contextualized across the world in different environmentally sensitive contexts, and we always aim to employ a multi-scalar approach where the research is realized across material scale, architectural, urban, as well as ecological. So you will see some examples of the recent completed dissertations this afternoon. And
yes, and we have a very amazing lineup of jury members here. Just to quickly introduce them, we have Enriqueta Labres-Valls, lecturer at Bartlett and founder and director of Labres-Tabuni Architect. We have Arthur Mamamani here with us, managing director of Mamamani Ltd and Fabrication Public, I think, yeah. We have Viviana Rosana Mushatella, director at Zaha Hadid Architects, and unit master at Intermediate 18 here in Architecture Association. And we have Andy Watts, director of design technology at Grimshaw, who's going to run our keynote lecture this afternoon as well. Welcome to all of you guys, and thank you for being here. All right, we have three groups. We're going to start sharp with Urban Village.
So, hello everyone. I'm Ghazal.
I'm True.
We made a video for our presentation. I hope you enjoy.
Yeah. And the title of our project is Urban Village.
The aim of this research is to develop an integrated urban and architectural system as a new sustainable solution to the problem which urban village brings. First, we need to know what is an urban village. Chinese big cities have faced large-scale urbanization and considerable rural-urban migration. Accordingly, new phenomena have been emerging as villages inside the urban area, including dense informal settlements. These dense settlements have brought chaos to their residents, but it is better to know what is the main reason for the existence of these buildings. For a more specific investigation through the domain problems in urban villages, Shupai village in Guangzhou serves as our case for the proposed methodology. Shupai village is located in Guangzhou, south of China, with its subtropical climate. In summer, there is hot, windy, and muggy weather, and winters are very mild. In the 20th century in China, the government imposed a rule according to which the agricultural lands that were previously owned by the villagers will be owned by the government for the purpose of developing and building the city. The process of occupying these lands by the government accelerated since 1980, and the villagers gradually lost their lands, which were the source of their income. Only the residential part of the village remained. A village that used to be surrounded by farmlands is now surrounded by expensive city buildings. The villagers who now only owned a house and had no income decide to replace their 1 or 2 story house with cheap and low quality 4 to 5 story residential units. In fact, they turned from farmers to landlords whose income was provided by renting residential units to immigrants and people who cannot afford to pay the higher rents in newly built urban units. This defective economic cycle decreases the quality of life of the residents every day. Even old villagers decided to sell their units to urban developers, a work that causes many homelessness and many serious plights. To overcome this problem, the project proposed an integrated urban and architectural system as a platform to enhance domestic and urban life quality in conjunction with insertion of agriculture as the village heritage. The solution that we think can end the defective cycle that has created this problem. These are the three scales which we addressed through MSc phase. Our experiment at MSc shaped around the combination of ramders and oyster shell, a material that is found in abundance in this area. Choosing ramders was because of several reasons. Ramders is locally available and cheap. It is a very good thermal resistance material which responds to this climate. Studying traditional Chinese building proves that using ramders was a proper material to respond to climate historically. Now in MARC phase, the integrated system is introduced in a more specific scales. Urban scale. First of all, we removed all the poor quality buildings and kept only the buildings that had historical value. The first way to insert agriculture was to use traditional agricultural farming, but we didn't have enough land for this purpose. Therefore, we decided to allocate only a number of desirable lands that receive appropriate sunlight hour as agricultural fields. As mentioned, having only traditional agriculture requires occupying a lot of land. We had to use modern agriculture methods regarding to provide maximum residential spaces, a method that produces more products by occupying less land. This method is a type of vertical agriculture called hydroponic agriculture. It only requires water which is available in our climate. Therefore, collecting and storing water became our entry point for the formation of our urban strategies. In addition, due to material limitations and our commitment to sustainability, we avoided the construction of high-rise buildings. Here are the urban objectives. In the first experiment, we ran a particle simulation on the mesh topography to analyze the flow of water across a surface. We reached several discrete curves, but the water collection system needs to be continuous. Thus, in experiment B, in order to achieve a continuous water collection network, we ran an agent-based simulation with the random population of water particles on the topography mesh following the achieved curves from the previous stage. After reaching the result, we selected the edges that had stronger connections across the site. At the same time, they shaped a continuous network. In order to prevent water waste, permeable water collector pipes are located alongside the channel. In addition, designing an appropriate cross-section for the channels enables for a better water navigation. For maximizing the water absorption, greeneries are defined across the channel. The defined hydro network needs to have hydro nodes for water distribution. These nodes should be as close as possible to agricultural fields and hydroponic units. In addition, they should be located in the lower level on the network for the water flow. In this experiment, we ran a GA optimization in order to find the location of these nodes addressing these three fitness criteria. The individual and non-Pareto front solutions with the average ranking of all the fitness criteria were selected. In conclusion, the achieved hydro network divided the site into four main patches which shape the basis of defining other urban strategies. The achieved hydro network and its greenery spaces provides an appropriate platform to shape the pedestrian roads. Therefore, in this step, a design decision has been made to define the main pedestrian network parallel to the hydro network. In order to define the program allocation along the site, we did a terrain elevation mapping. This functional distribution brings the opportunity to define the transportation network in a circular arrangement inside each patch, which they are connected to the important boundary streets and provides an appropriate accessibility to the site. According to elevation mapping information, we selected the location of residential areas in high elevation parts for maximizing the view of the residential units, semi-public function and public spaces located from the center of each patch to the boundaries of the village respectively. These semi-public areas are mainly for hydroponic agriculture, and public areas are for public activities such as education, workshop, and leisure. Landscape. The ambitions for designing the landscape or local scale are maximizing ventilation for a suitable response to hot and humid climates in hot seasons, spring and summer, maximizing appropriate sunlight hour for residential clustering in winter, maximizing the amount of sunlight energy received in agricultural fields in winter. In order to locate the programmatic functions on the local scale to achieve the mentioned objectives, it was important for us to define the morphology and aggregation of buildings including residential clusters, hydroponic agricultural buildings, and other public functions. Therefore, we set a GA optimization as our experimentation in this scale to optimize the landscape objectives. As we investigate the traditional buildings in this region, we understood that the arrangement of mass and voids were in a circular arrangement due to the environmental consideration. Therefore, with the help of magnetic field tool, we set attractor and repeller points as our mass and void elements respectively. The next important step is to define the morphology of the mass in each zone. In a feedback loop with architectural scale, we know the approximate bounding box for our clusters. They can be scaled in a defined domain, rotate, and have different heights. The morphology of the hydroponic units also can vary in regard to satisfy the objectives. The achieved curves from magnetic field experimentation gives us the opportunity to define the shape of our other public functions. This morphology is defined to respond to structural consideration using numbers. 100 generations, 50 individuals were run in the GA optimization. 50 Pareto solutions are selected from the individuals. Among them, individuals met the average values in fitness criteria 1, 2, and 3 were selected as the basis for the following experimentations. At this stage of the work, with the information we had in progress from the rest of the project, we tried to draw a primitive picture of what we might reach at the end.
For the material system, we have three objectives. One is more lightweight, one is thermal insulation, and one is locally available materials. Based on the MSC phase, we already have the specific renders materials, and for the lightness of the structure, we introduce the timber in the MArch phase. And in the architecture system, we also have three objectives. One is ventilation, one is self-shading, and one is hybrid structure. We start from the core of the building. In the horizontal direction, we introduced a wrapped around architecture layout, which contributes to the ventilation of each flat as well as self-shading. Vertically, it is ensured that the roof of each flat is set back from the floor slab to allow the internal ventilation throughout the building. After defining the basic concept, we did the overall frame structure of the building, with the columns and beams made entirely of timber. For the flat, we have summarized the 6 most common types of flats based on the fixed floor area and floor height. The angles of the flats varied between 30 degrees and 120 degrees in 30-degree intervals in order to fit the frame structure set in the previous step. Then we get the primitive geometry of the flat. For the morphology of the flats, we did form finding according to material and ventilation. The flats are mainly made of renders, which is a typical compression on structure. On the other hand, the Venturi effect was introduced to achieve natural ventilation. Based on these two aspects, we introduced the conical vault, which meets the needs of material and ventilation, and which can be understood as being formed by inner contour line and outer contour line. In the next step, we run FEA on the 3 forms of vaults. By comparing the advantages and disadvantages for the inner contour line, we chose the third form of vault. where the forces on both sides will make the structure more stable, and for the outer contour line we chose the rounded board. So the morphology of the top of the flat is formed by these two types of the contour lines. In the aggregation setting, we set up two rules. One is all different types of the flats are interconnected around the core, and the other one is each flat is offset outward by a random distance. And the next step is the genetic algorithm. We have three fitness criteria. The first one is max self-shading in summer. The second one is minimum displacement in structure. The third one is maxed void space in the middle. After completing the genetic algorithm, we extracted the genes controlling the bounding box as the training input and used the other genes as the training output to perform the machine learning. In machine learning, by changing the bounding box, we get the corresponding building form. It provides us with a good start point. In the site analysis, we were given a number of such values. When we apply the machine learning to the site, it provides us with the specific building forms. In the next step, we connected some of the buildings on the site and created an agriculture area in the center of the connection. This agriculture area will be constructed from timber structures, which will also support the entire floor slab together with the structure of the residential buildings.
Here is the construction detailing of hydroponic agricultural units.
For the construction detailings, there are two objectives. One is modular construction and one is self-shading. For the rammed earth components, each component consists of the slots and protrusions to allow interconnection between them. At the same time, the thickness gap between the components is used to provide the self-shading. And this is the detail of the vault components, and we can see that how these slots and protrusions work together. This diagram shows the construction of the flat structure. To be more specific, rammed earth occupies a large part of this, including rammed earth wall as well as the rammed earth components. In addition to this, there are also some timber frameworks with glasses, as well as the timber sunshades. This diagram shows the construction sequence, starting with the construction of the frame structure, followed by the assembly of the rammed earth modules in the flat units, then the installation of the timber frameworks and the sunshades in the flat units, and finally is the construction of the rainwater connection roof.
A roof is attached to the top of residential buildings, which provide the possibility of collecting water in these units with the help of pipes. Parts of the water is used by residential units and the other part is stored for agriculture. This roof is also used as insulation against rain. The water collection system expresses the relationship between the urban scale and architecture. The beginning of the design started with water collection system, and this image shows the different parts of our design, how the water has arranged them together. As a summary, we must say that it is not possible to provide enough housing units for all the previous residents, but this complex can provide a residential and economic platform so that with collective planning, all the previous residents can benefit financially from it, rather than some who cannot live in the new village. From an economic point of view, they can provide at least their needs in the city. As mentioned, in addition to residential units, this complex has semi-private and public functions. Hydroponic greenhouses are suitable for workplaces for a number of resident members. Also, the produced products can be sold in public areas near the border of the village and the city. Also, public spaces will be a possibility to hold regular workshops in order to share the experiences of villagers with city residents. This activity can also be a good source of income for village members. In addition, it provides the possibility of developing this sustainable experience to other parts of the city.
Thank you.
Thank you.
Thank you. It's a lot of work, so it's just digesting everything and trying to give something helpful. I know this is sort of finished and you have a critical piece to write. There's a lot of really good stuff, so I'll focus on the stuff where I'm critical. A lot of the simulation, like when you showed the agents, which defines the sort of landscaping strategy, it maybe lacks a little bit of what's going on there type of reflection. You know, I'm just curious if it was just the rainwater that directed stuff, or if there were more criterias, and also, you know, what are the points of control that you can then recontrol, or do you have to rerun agents to? Is there something that you observe here from your own critical mind, not just the tool? Because what will happen in practice is that as much as we can use some of those tools, there will be a moment where we have to compromise the tool, and so therefore there is no choice but to kind of have a sort of human reflective approach to that. And this, maybe it will help if you had the sort of, I would say the sort of, you know, curve-based version of that you can be more manually critical on it with labels and clear understanding of it, rather than just the simulation and that's it, and then we use this to populate our stuff. The other thing that I'm really missing is the making of those domes, you know, just at least some attempts to see how the oyster shell, it's the lime in there, right, that sort of solidifies the earth. You know, it doesn't hold tension at all, right? And the domes are transitioning from compressive only to a more regular dome with straight lines, which means there will be tension in there. And so I'm just curious for you to see the point of failure of using that, because a lot of the building is going to end up, I mean, you say it's timber, but there's a lot of surfaces, there's a lot of cantilevers, there's a lot of weight because clay or any earth material is very heavy. So how does that timber relate to the dome? They can be quite kind of separated, and so it's hard to understand how the entire system will work together as a whole rather than separate units. Sorry, I can keep on going, but those I think are the main points.
Thank you.
Thank you.
Thank you so much.
Thank you very much for the presentation. Of course, there is a lot of material here out of 1 year of work. I have a few maybe suggestions for you. I mean, while you were presenting your project, I had the impression that this project is a lot about tensions between the existing city going really high and those villages, social tension, meaning economic tension between the rich and the less privileged, but also in the way you develop, you then discover that there is, you know, competition in between water, pedestrian, cars. I wanted to ask you in regards to you know, assessing your work now after finishing it, whether you think that the final result is you know, giving a solution that could be applied in this location or in other location or in other villages, and moreover, how you think the people will inhabit. Your two agents are actually people, but also the greenery, the ecosystem with the agricultural part. How do you think that you know, your design proposal will have an impact on those big tensions that you have shown us historically in this area? You don't have to have the perfect answer. It's just, I mean,
Yes.
out of all of this, one thing that you think that it's a positive impact in your proposal.
Can you ask again, like the?
Okay, I'll ask again. So,
I'm sorry.
your project, right at the beginning, it gave us an understanding of how complex is this particular setting of villages inside big cities. This is not happening only in Guangzhou. This happens in many, mega cities in the world, where leftover pieces of spaces are then, utilized by people with very precarious constructions. And you talked about a lot of, tension in between the urban fabric all around, from the point of view of pedestrian, cars, water, and moreover the economic one. So if you have to select out of your project, let's say the one aspect that with your proposal you had a more positive impact, what would it be?
Like the overall tension, like the overall ambition of this project is to address three important aspects, like environmentally, socially, and economic. But according to what we did and the studies that we've done, I think the most aspect of emphasis is most likely to the environmental aspects, like the water collection, and then we are addressing also the social, social impact and economical impact. But the most emphasized thing is the environmental consideration that can respond to the climate ecology.
And then maybe it would have been nice to see at the end how, taking all of the area, the GFA, the area that you cover with your project and what you are proposing, to have some data to really be able for us to assess, okay, we went from this kind of situation to this other, and then there is something that you can, because I'm sure you can get us an idea of how much with your intervention vegetables you are going to get from the hydroponic system, or how much greenery is more for pleasure, and how much. So it is quite important if you somehow decide that your primary client is to create a better environmental condition, then to give us this information back.
Okay, yeah, thank you.
I have a few questions more, but I'm going to pass them. We can go back.
Well, first of all, thank you very much. I think echoing what Viviana and Arthur have said, there's a huge amount of work there. What I would say is that, listening, and I've seen you guys present this before, but I still think as part of this presentation, there are some gaps, there are some leaps of faith that you are kind of requiring us to take. So, this idea of, okay, you're going to essentially bulldoze however many thousands of homes and then put farming there. It has its own problems, but I'm going to gloss over that for now. But there are decisions that are made without necessarily telling us why you've made those decisions, or what those, or even fully telling us what those decisions are. So you've decided this is going to be an urban farm. What is this farm producing? Is it, you talk about agriculture, you don't just do agriculture, there's a whole ecosystem around that needs to be considered, including actually what is the produce, what is the output of this, because that will affect the whole typology. And you don't really talk about that, you just say, it's a farm, we need fields. And I think we need to be a little bit more clear on that. Likewise, when you start to zoom in to, the residences and even the greenhouses, you basically say, for a one-bed flat or one-bed apartment, you need X square meter, but you don't really talk about the program of that. And actually, a big part, and actually a really striking part of what you described at the very beginning as part of your introduction, was around the fact that there's been this, hyper-dense growth of this kind of residential area of housing, which results in poor quality. It results in housing basically falling down. how are you improving on that? How are you improving on that quality of life for those few houses that are left in this area? I think you really need to kind of describe, and touching on what Viviana said, it's about actually what is the outcome of this project? What have you improved? What can you turn around and say, this project has achieved X, Y, and Z? And I think you really need to nail that landing, because I think you've made a lot of decisions and then, it's just, that's the end. But you need to tell us what you've accomplished as part of this. So there's that, and just a very minor point as part of presenting, and I'd say this to all the groups, when you talk about what you've done, don't talk about the tool, talk about the task. Yes. You mentioned GA, you mentioned FEA, you mentioned machine learning. You don't say what you're doing with them. And I think you need to.
Yeah.
Yeah.
Yes. Thank you.
Okay. Thank you for your presentation and for your work. I want to reflect on what it means to intervene in an urban village. You come to a context that has its own dynamics. It is already a system that has its logic in the city. It also hosts low income people in the city. So there are certain dynamics that are happening in urban villages. Then you propose a new urban system that somehow has the ambition to have certain intelligence by reading certain environmental conditions. But then you end up being quite deterministic in the way you apply the system. So, for example, what is the resilience that the system that you are proposing has? And I think it will benefit you a little bit to grasp from system dynamics concepts to understand what it means to implement an intelligent system, or when you try to integrate one system, which is the urban village, with your new system. So what happens if all the shops that you put at the periphery don't work and you have to put them inside? Can your system accommodate that? What is the hierarchy in the decision making? So, I mean, it has the benefit that you are presenting a model that it's driven by something different than traffic, because most of the urban models, as you could see in the periphery, are driven by the road system, and you're trying to present an alternative as a landscape driven. But I think in order to present an alternative as an intelligent urban system, you need to show its capacity to adapt to different scenarios and not to be so deterministic. Which could be that, listen, you cannot demolish all the urban village, just half. What happens? Can you do that? How will your system respond? What happens if at the end the shops are inside of these things instead of in the periphery? Can your system accommodate that? And so feedback loops, iteration, and concepts that have to do with complex adaptive system are missing in your proposal. And it's just a pity, because with the tools you can achieve an intelligent system, but without the conceptual framework, you cannot really present an intelligent urban model.
Thank you. Thank you. Thank you so much.
Not just a quick question about this addition on top of the on top of the cluster of residential building, that is your water collector roof.
Yes.
Have you looked into using your doubly curved roof to do the same job that this quite heavy superstructure is doing?
Yeah, mostly like because of the core that we had in the middle, we decided to design a system that also prevent the rain inside the cores. But another option was for us to have the double layer, for the water resistance. But we wanted to also address the core inside each clusters. And then at the same time, it can collect the water because it's one of our main objectives in the urban scale, so it can also address these objectives as well.
It's only because at one point you show very quickly the kind of historical typology of housing that is not the hutongs, it's called in a different way, and I keep forgetting the name of the circular arrangement in villages, historical villages in that part of China, of course. But the way they were working was that effectively, yes, you have the residential on a ring, and then the central part was dedicated to, you know, having your own animals and do some farming and grow, and you know, it had a very, very important meaning for the community. So the kids were, you know, growing up as part of a village more than just as part as a family. In your case, that role, let's say, it's taken now by something that effectively you can resolve from a technical point of view, collecting water in a much simpler way, and yet leaving the opportunity also having double facing residential that will provide much better internal ventilation. We are talking about Guangzhou that is always hot and humid, where ventilation, as you have done in your proposal, is very important. But by placing that element, you are effectively missing completely the normal effect that you get when you have a double. You can open two windows, one there, one there. So I'm just trying to somehow point out that maybe this gigantic superstructure that is taking a lot away also from this idea of greening up this area, also visually, it might be a bit of something to reflect on. Yeah.
Thank you.
Maybe because I was trying to be fast, but I think everything that was said is really, really important. And there's one thing I just want to mention is just urban village and just that name. I mean, villages are urban, and you know, and it's a bit hard for me to understand what makes this a village, or what made what you actually in fact demolished as a village. What is that notion of village, and which part of it is it the fact that it's separated items? Is it the fact that you're using a topology that was more vernacular in the time of where this city was a village? Or I think it's just concluding on that image. I'm not sure, apart from the roofs, you know, what creates the notion of a village. I think this really needs to be clarified.
Like mostly what we thought was the introduction of the agriculture as the deep root of its heritage of the village can give the meaningful definition that what is a village here and what is the city, and how the housing materials are responding to these functional definition. Yes, but we should clarify it more. Thank you.
Maybe start from someone who lives there and what they experience and how they create community, you know, because now it's really giant floor slabs with some plants on it, rather than just what does it feel to be in there. Yeah.
Thank you.
Thank you, guys, and thank you for all the comments. I mean, this applies to all the teams, actually. You can use all of these comments for your final critical reflection paper. They're all very important to kind of reflect back on the thesis itself, and, you know, what works and what could have been improved more, and how to evaluate what you have done, basically, is very important, right? And this, I mean, proposal that you have generated for this specific site, for example, could it be regenerated somewhere else. That's also part of adaptation, what Enriqueta was talking about. So it's important to kind of think about these nuances. But thanks a lot.
Good afternoon, everyone. So we are Team Biobot, and this is Manya, and this is Anna, and we're going to present our thesis design dissertation.
So to begin, the number of proposed homes within London's Greenbelt has doubled in the last 2 years to more than 200,000. Infrastructural land take, urban sprawl, and economic overdevelopment have led to the physical disintegration of continuous ecosystems, habitats, and landscapes with the extinction of existing plants and living creatures. Moreover, green coverage depletion has decreased resilience to climate change. This urban heating not only diminishes the survival of biodiversity, but also curtails human activities, recreation, and quality of life, with over 9,400 premature deaths attributed to poor air quality annually in London. The green cover in London has drastically decreased over the last 40 years, with 20% increase in carbon NO2 levels, while fuel-consuming vehicles are major contributors to urban noise. Subject to high temperature differences during summer and winter months, heat island as a contributor, also induced by energy wastage and heat generation, mapped across different zones of London, identifying Soho as a high-risk zone. The high-risk zones are mapped through their high energy wastage, high heat emissions, high air pollution, and lack of green cover, which can be facilitated through nodal intervention, that is production of biofuel and electricity to balance energy wastage, collection of water, inducing thermal regulation and air filtration, as well as the protection of species to cater to green tissue fragmentation. A new green technological energy network is needed, which can grow from these intervention points to create a sustainable solution, as it makes its connectivity back out to the green belt as a dual facilitator to fragmented landscapes.
These functions have been distributed across the thresholds of interstitial zones found between the built and the unbuilt spaces, where symbiotic habitats as architectural intervention can be intervened for the protection of species, whereas green public energy powerhouses can be generated in urban interstices for the function of collection and production of electricity and biofuel. And to cater to the function of filtration, double skin facades can be intervened. The generation of the technological ecological machine network has been done across 4 scales. First scale is defined under an urban green network. Second scale defines the architectural resolution. The third scale defines the modular design. And the fourth scale is defined under the material exploration in order to facilitate to the design goal of the project. About the network aggregation.
So as patterns occurring naturally have always been adapted to the variability and change through environmental pressures, one of which is the examples of diffusion-limited aggregation, its tendency to bifurcate as highly functioning network, optimized through its generative growth, addresses multi-directionality and nodality at the same time. Therefore, the prerogative of the project is that it be in symbiosis with the scale of morphological growth development. So to facilitate the growth of the network, the truncated octahedron has been selected as a primitive, given its hierarchical organization as it relates to the different faces, as well as their locations in Cartesian space. The central node becomes the brain of the module, which is outfitted with different sensors to respond to environmental stimuli. The truncated octahedron also has associated growth to deduce spatial implications, which are assigned by the designer in extreme scenarios, such as self-shading, canopy, diffusion, lateral connectivity, all through the prioritization of its vector faces.
The truncated octahedron could have associated growth phases to deduce spatial implications, which is further leads us to the development of a material exploration phase in which we want to facilitate a material that can induce the growth of a living green tissue in order to address to the goal of fragmentation, whereas also induce carbon adsorption. This experiment was conducted further using timber sawdust as a main material, where achievement of goal of porosity was the main aim. Green tissue growth, water retention, thermoregulation, carbon adsorption, and structural strength and its decomposition were further formulated. Timber sponge as a material was formulated through certain experiments where porosity was achieved for almost 55%. Green tissue growth was occurred in 2 months. Water retention for 3 hours, thermoregulation with the lower thermal conductivity, and good surface bonding. The structural strength capacity was 18 kilograms under tension and 85 kilograms under compression. The decomposition of the material was calculated to be over 20 months under extreme environments. In order to cater to the function of filtration, protection, production, and collection, the basic materials utilized for the production of the Biobot were timber, sawdust, moss, and algae. The timber material was used for the structural scaffold, and the sawdust material was used for the timber sponge morphology, whereas moss was utilized for the production of electricity, and algae was utilized for the production of biofuel. Further, the biobots were developed in order to cater to these functions. The first bot developed was the alga bot that constituted of continuous algae pipelines. The aim to develop this morphology was to increase the surface area to volume ratio in order to maximize the sun exposure for the photosynthesis of algae.
And within the module, we have a living tissue on which moss is being grown, which acts as a filter and also creates shading while the module is being rotated to reorient itself towards the sun. The tubing is set up to be a clip-on part of the arm in order to facilitate the modularity of these simplified assembly systems across all modules. And here in the HydroBot, which is our water collection module, the main aim was to have a high surface area for water collection and to identify channeling throughout the module arrangements. And in this particular one, the bottom has been rounded while retaining its edges because the bottom is made of the diffusive living tissue material to dissipate water throughout all the modules that it is connecting and facilitating with, as opposed to the half module, which is the HydroTerrabot, which incorporates the shading of the moss below the plant modules for vegetation, which are connecting to it.
In order to facilitate filtration, Osmobot was generated. The main aim to generate this morphology was to create highly membranous morphology in order to capture particulate matter from the air. Computational fluid dynamics was conducted in order to facilitate maximum flow of air inside the module to capture maximum particles. FloraBot was generated in order to facilitate the growth of plants and green tissue under the function of habitation of plants. The main aim of creating this morphology was to maximize the surface area of the planter pockets in order to receive maximum circulation of water, whereas equalize the sun hour radiation for plants in order to receive sunlight hours for the plants during the day.
So further examined in this module was the idea of incorporating another biomaterial, which is clay, as a porous material capable of absorbing the water that is being diffused from the other water collection HydroBots, which is connected to every 8 of these within the network. And the vegetation has been studied in order to make sure that there is an equal balance between rooted plants and rhizomatous species, as well as those that are endangered in London specifically.
Further, Terabot was generated to be made out of the moss morphology and was supported by the timber sponge differential algorithm model. Thermoregulation was conducted at 3 different stages in which the sawdust structure, the timber sponge structure, and the inner scaffold created considerable amount of heat regulation.
And so in this one, by inverting the faces inwards and yet still surrounding them with the extruding arms for connectivity, you end up designing basically a pocket, and by applying a living biotissue to the exterior of the framework, which is clad in the sawdust mixture, it will actually engorge over time, and therefore it sort of simulates species to use it for habitation and shelter as it grows over time. So understanding the rate at which the moss actually proliferates on it is important.
In order to create the plant pocket morphologies, robotic extrusion techniques were formulated. Continuous morphological structures were created, although baking was utilized as the main strategy to develop the timber sponge morphology. The baking structure constituted of cornstarch, sawdust, and yeast as the main materials in order to attain porosity. The baking was conducted under a temperature of 200 degrees Celsius in an air drying furnace. And since the structure the timber sponge can be molded into any form, that's why it was applied for the differential growth morphology in the biobots. The biobots can be categorized under the 4 functions: the production function, the collection, filtration, and protection. The Terabot is categorized under the protection function as it facilitates the growth of moss as well as indicates housing of species and by creating an ecosystem. Production of algae helps in inducing the production of biofuel, whereas collection induces the collection of water and collection of heat, whereas the filtration module developed as Osmobot filtrates the air, and the protection function is again categorized through Terabot and the Florabot. In order to conduct this experiment further into the technological urban scheme development and to induce participatory aspect to this project where people would consider ownership of this project, an urban environmental scheme was generated. The first step includes the environmental mapping where a high-risk zone is figured. Next, an architectural resolution is produced by the architects or the computational designers who are generated or involved behind this process, where this entire process gets developed through a web development or an application platform where the users can participate and get indicated about high-risk zones, where these biobot development activities become a communal part where people can come together on certain weekends and develop these morphologies to as an initiative for environment protection. The Biobot assembly was designed to take part in 2 days on the site, whereas the third space communal activity was generated. Real-time interaction with biobots was also inculcated, and repair and replacement was induced for 2 years.
And so when we arrived to selecting a specific site within Soho, we had 2 to choose from at varying scales, and one is Soho Square itself as being part of an urban fabric and owned not privately. It's interesting though that it is a square and it is only constituted of about 4 trees. And the other scale of our intervention was an interstitial space, which is actually commercial, and it is prone to different fluxes of circulation at all times. And so what actually connects these together is the identification between interstitial and grade 1 and 2 preserved buildings and how we can navigate through them, particularly because the shortest distance between 2 large transportation hubs is actually it culminates in Carnaby Square, or Carnaby Street rather, which has upwards of 110,000 people visiting it daily. So it is actually disrupting thermally, having that many people shift through the square.
Further, this area was mapped through functional distribution mapping, where environmental parameters such as green visual proximity, daylight access, particulate pollution, wind vector hits, and pedestrian flow was mapped. These parameters were weighted through voxel grading method, and the clusters were formed through Kohonian cluster self-distributing method. The weights were assigned to the 4 functions: the production pods, collection pods, filtration pods, and protection pods, according to the prioritization of these environmental parameters, where production pods require more daylight access as compared to the collection pods, and where the filtration pods require more wind vector hits as compared to the other pods. So by description of the weight vector of the voxel weighting method, the distribution of the function across the site was formulated. Further, the DLA morphological generation was designed, where there
was a certain amount of constraints that needed to be implemented within the algorithm to prohibit it from growing absolutely anywhere it wanted to, and so we decided to limit those to reasonable architectural sort of interventions, for example, window constraints, which cannot block the exposure to light nor vantage points of people, structural constraints, which took into consideration cantilever distances between buildings, sites that we wanted to intervene with, road constraints, which would limit otherwise traffic or pedestrian flow, so those were to be avoided, as well as the grade 1 and grade 2 building constraints for consideration. And so when we began to associate directionality of vectors with implied spatial conditions, we identified upwards growth, lateral, and lower lateral, and those began to be recategorized as upwards of having maximized vertical connections to obstruct wind. Lateral, but still upwards, was maximizing lateral connections to create shade, versus in the downward direction for green tissue attachment, and maximizing lateral attachment for ground support.
Further, a 3D grid was analyzed in order to assign the position and functioning for the Biobot morphology development and the network development. Green tissue proximity, wind vector occlusion, sun vector occlusions, and unlikely path analysis was conducted. The grid was weighted according to these parameters, where each voxel point received the weight for the growth of Biobot. A cumulative weight analysis was also conducted in order to test the 4 parameters on a cumulative basis. The spawn points for the generation of DLA network was generated, where highest green tissue was the spawn points, the highest wind vector hit were the spawn points, and the highest sun hour, and the unlikely paths are the attractor points. A DLA network was generated after conducting the spawn point attractor point analysis across the Soho Square. 4 different parameter DLA were also generated. In the first option, where the green tissue parameter was kept as the priority, more connections to the ground are observed. In the second parameter, where sunlight hour, maximizing sunlight hour radiation is the priority, more canopy-like structure is observed by creating more shade on the ground. For the parameter number 3, which is attachments towards the ground to inhibit species, is observed as more heighted morphology. For the parameter number 4, which is high wind vector hits, is observed as a more steep canopy-like structure in order to address wind regulation. Later on, the final morphology was created by taking an average of the 4 parameters, where it was observed that sunlight hour and wind vector hits were the major parameters that affect the morphological changes.
And also there were certain structural limitations that needed to be rationalized on site when implementing so many modular pieces at the urban scale. So within the existing ground, whatever the cladding of it actually is going to be retained in the process. So the footing locations are identified against a grid, so very easily we can map out 1 meter by 1 meter and identify where we're placing these. So the cladding is removed, the location is marked, the footing is placed, and then we cover the footing to sort of imagine that these interjections really are not disrupting the space as much as it would appear at this scale. And so we're also, the modularity of the growth of the system also works to sort of cover any unsightly things that we are hoping to hide as designers, while also trying to acknowledge our site. So for example, draining back gray water collection into the existing storm runoff management.
Further architectural detailing was conducted for the collection pods in the Soho Square. The first pod was the algae collection pod, which was designed as a user interactive space where the users could be indicated to participate with this morphology. The first participation was in community building, where people could get together to assemble these biobots to facilitate the environment. The algae module is, again, has a timeline, which is an assembly timeline of 15 to 30 minutes per module, and replacement in every 15 days. The algae circulation has to be conducted in every 1 hour in order to receive maximum sunlight. The moss growth occurs over 2 months, and the timber sponge decay occurs over 2 years. The first indication happens through the first cycle, transmitted through signals to the users in order to generate electricity.
So in setting up a system that can get deployed anywhere on any site, it's really important to simplify it. So actually 60 cyclists over 60 minutes can generate enough power to fuel 30 homes. And so again, we're looking at excavated stonework, battery generator on a stand, a driver belt, and participatory cycling, which connects back to a collection pod located underneath the columns, and the columns are centralized in order to facilitate ease of access on the site, and they get drained per their cycle and shipped off. And by understanding the algal bloom against its spatial implications of how many people are coming through the site, how many people are actually commuting through, and how many are willing participants, it gives us an idea of how the space changes over time. And so also at this scale of intervention, we have participatory practices at a 1-to-1 scale. We also need to acknowledge that the algal biofuels are generating back into the grid to provide self-sustainability and powering nearby charging stations. They do get shipped off, or they can be in a participatory practice. Exxon has made huge promises to develop biofuel conversion generators in London, but as of yet has not. So we are anticipating that the proposal of these will actually gain traction in the upcoming years. And because of the user participation in the scheme that Vanya had outlined, we're able to track the bloom at all points to know that if you are participating, you'll get a notification, and therefore you'll know that at that moment in time where the spatial temporality of a microalgae is.
These are the renders of the Biobot morphology that we generated for future scope. The second pod was the moss pod. The moss pod was created for the production of electricity, where the moss voltaic was used as a study. The moss Through the photosynthetic action of the moss produces electrons where conducted through cathodic and anodic tubes can generate electricity and be used as electric pods and be attached back to the urban power grid.
And at the same time, we're understanding also how these living tissues transcend over each other in time, and so they're more likely to encounter species interaction. And this is a look at the vegetative pods, which are actually also serving a twofold purpose of mitigating the air circulation at ground.
This is the cyclic process of the collection pod, where moss
actually goes through a process of propagating first. It dies off, but it also equalizes on the living material because it consumes toxins and molds and trace elements which are found in highly polluted areas such as Soho. And by understanding how it grows in between the actual modular connections, we can understand how self-shading is happening to thermoregulate underneath.
Similar analysis was conducted to generate network for a building facade, and the most optimized network was utilized further. Design considerations were taken into practice, and it can be observed that the facade was used for filtration and also for thermoregulation.
And so when we end at the green belt, where these modules ultimately do get deployed also to connect back with green tissue, we hope that anticipating its growth can actually inhibit species. We can design for bees, squirrels. As comical as that sounds, you can establish your decay rate of material along with fungus that's there and sort of equalizes habitation for the encroached upon fox. And then at the end of its decay cycle, we understand that what we're left with are these structural remnants which can get picked up and recycled back into the next Biobot system. And so we've also considered that in order to advertise a sort of purification system like this, which is doing many things at once and reconnecting green tissue and fragmentation, we also have to quantify it a particular way. So by identifying the amount of modules, their carbon absorption, oxygen production over the course of 1 year, in literal terms, we can quantify that the project has viability.
And it was observed that 420 particulates per.
We're at the highest level of carbon right now, historically at 420 parts per million, which was previously 417.
Yeah, thank you.
There is a phenomenal amount of work, and there are a lot of very good qualities in the proposal. So I want to start by acknowledging that. And actually what I have is more a suggestion of an opportunity that I think it's there in the project and you could pick up on this one. And it's the fact that when you present the section of this Biobot and you show this Arduino, actually a microprocessor, right? If you look at how this technology has developed, they already have their own internal capabilities of machine learning. They can communicate through Bluetooth and Wi-Fi. So actually, you have there an element that can sense, can actuate and communicate between each other. Yeah, meaning that I was a bit curious about the different colors and the different roles that these biobots had, but actually this doesn't have to be an static thing because they could sense each other, they could like understand somehow their own position within their own structure, and they could actuate and adapt. Yeah, and this was something that was not in your presentation, right? It was more presented as an static element. So this is something that is there and is fantastic. I think it's there. You just didn't click on that. But not only that, is that it also changes the way it relates to us as people with our devices and the way it can communicate with us. So more than if people want to build it or doesn't want to build it, is that it has a presence in the digital world. So it can have a social presence. And yeah, but for further research, I guess. So, but it's a very nice piece of work, I think. I enjoy it. I was telling Milad, I got hungry with your timber sponge. It was really suggestive. It was really nice.
Brilliant. Thank you very much, guys. I thought that was quite an enjoyable presentation. Oh, I like these images. They're quite nice. What I would say is that I think one thing that struck me from your presentation is, you know, your thesis is very much, whilst it's in the realm of architecture, it's very much a product-based dissertation that you've kind of produced. And because of that, you know, the way you presented, it kind of struck me almost as if this is like some kind of Dragon's Den situation where you're almost pitching to us, you know, what this could be. And because of that, I guess that's kind of influenced the questions that I got for you, which are more around things like governance and organization, logistics around this thing, because you've essentially got this product, this suite of items that can be produced. But have you given any thought really as to, you know, logistically how that might happen? Because, you know, even as you talk about the simulations and you see these numbers going up to 7,000, 8,000, that's a vast amount of these things that have to be produced. So is that done through some kind of, you know, some kind of social exercise where the public are trained in how to do it, or who actually owns these things? You know, they're in a public space, but then you talk about them climbing up a building. In that case, are they owned by the building owner? And I think that that's quite a fascinating thing, because at that point you start to see different people's agendas really starting to influence this. You know, you talk about the analysis that you've carried out is very much based on what you think is the ideal situation for that public environment. But if I were the owner of a building, maybe my agenda would be different. Maybe I want privacy, so it's all about shading, or maybe I want to reduce my water bill, so it's all about water collection. And I think at that point you start to really see different users and different personas have their own take on how this should be deployed. And because of that, you know, that's why I'm thinking about this like almost a product proposition. You start to think, okay, how do you then market this to individuals? You know, you give them control over what this could be. Is there then maybe a user manual that basically tells you how to deploy it, and there's a digital layer and all of that stuff? Because I think it's a very, very rich proposal that you put forward. But what it's missing, I think, as a client, it's missing who this is for. And I think you really need to kind of, you need to have that in place, because that informs the entire agenda. And I think it is very interesting, but there's just, for me, there's that one gap. But yeah, thank you very much.
Thank you.
Thank you very much for your presentation. I second everything. I really enjoyed the presentation, the drawings, and the story behind. I have a few questions, but maybe that I want to start with something that you said right at the beginning. You were talking about, you know, how nature is actually fighting for, you know, getting the best lighting, talking about the branching system of a tree, lighting or water and so on. And I then thought about it when you then presented each one of those modules that are doing something very different from the one that is to grow actually some vegetation, to the one that are mostly to do with energy production, and the one that are maybe for harvesting water. And then I went back and thought, okay, but what could be, let's say, this analogy between, let's say, the natural system and your system, and why then each one of those modules, they have to have the same morphological aspect, the same, put it this way, shape. And that eventually the differentiation that nature does is exactly this. There is a part that is more structured, the other one that is to do with water, the other one is with how to filtrate the light. And I think maybe in a way, for as much as there is a lot of science that you applied in the way that they aggregate to each other, the fact that at the end everything is reduced to one shape and one component that has to do a lot of things, it might be maybe the weak point of your project. And this links a bit to maybe in the future, but I would have really appreciated if there was some thoughts about seasonality, meaning that aside, one of the reasons why we're losing green areas in London is not only because of speculation by developers. It's also that in the past maybe 5 years, summertime in London have been quite long. Everything dries out. A lot of bushes and vegetation are dying. And somehow showing how your system could be something throughout maybe the two extreme seasons, winter and summer, both when you apply it on the facade of the building, as Andy was saying. I mean, maybe during the summer you want more screening, and during the winter you want to get more natural light inside. Could have been quite an addition in terms of how the performance of your system could be reassessed and maybe reconfigured according to.
Cool. Same, I really enjoyed it. They're very beautiful bots. I'm really missing like physical experimentation. I don't think I've seen a single model, or especially when it comes to living systems and like complex geometry and like, I think this is really important that you test that, because otherwise it becomes very image-based, and I think it's really important. So I put this top of my list. Second is the grid. This module is space packing. It's one of the potential space packing module. It means that what you start with is a giant grid, and then you remove mostly to some extent, right? Because it's one orthogonal grid. It'd be nice to see how you deform this, or how you let it grow a bit more freely. Talking about nature, I think nature has this ability to do that. And so it'd be nice if your geometry could do that. You start with a triangular grid. Really, this is an expansion on that. But the triangular grid can have a scissor behavior to it. So why not let that? I know it's a bit harder to simulate, but it might be interesting. It might give you more possibilities to play with the structure, the grid itself. And then finally, the biofuel. I love that you're involving people with their bikes. I love that there's an app. It's a fantastic product. I think you say Exxon promised to do that in London, but they haven't. I think here's your client. They're all trying to invest in biofuels and so on. But there is one issue with biofuel, same with biomaterial, is the quantity of mass that you need to produce, 1 liter of fuel, for example. It'd be nice to have this understanding. I know that, for example, if it's an abstract, but to replace all plastic with bioplastic, you'd need to use like 50% of all corn production in the world, for example. So how does this relate with your fuel? How is the fuel generated? Why do I still need to cycle? Why are your bicycle not electric, and why are they not powered? I got a bit confused between the practicality of producing that and the need to generate electricity. I love it, but I'm confused. So I think maybe there's there's something there. I mean, you mentioned, maybe that's more of a question. You mentioned clay as as a biomaterial, but clay is inorganic. Clay is it doesn't have organicness to it, so it's not considered a bio. I'm curious to see if you have materials that can actually compost, as opposed to, yeah.
Can I add? So we conducted an entire sawdust timber sponge experiment in the MSc phase. So that was the only video that we didn't play, which had like the total proper bending tests and yeah, it's the video that had everything.
Okay, so sorry. Okay, maybe next time just bring your models.
Yes.
You know, yeah.
Our models are upstairs.
I mean, it's a hard one to make, and it's gonna have lots of water, lots of stuff. So any robotics that deals with just like so much moisture, I mean, it's an interesting, yeah, and they're really beautiful. So I'm just curious to see how you make this thing. Yeah.
Yes, we have our material if we can bring by the end today. Yeah.
Good.
Thank you very much.
Well, good afternoon, everyone, members of the jury, fellow students. We're MacBoy. MacBoy stands for Refuge in Mayan, which is where we're conducting most of our studies. So we began by looking at hurricanes, and specifically the Atlantic hurricane season. So each year, the Atlantic storms impact the Yucatan Peninsula in Mexico, which is our area of study. And with global warming and increasing temperatures, these storms are becoming more frequent and stronger. We chose to study the area of study in Mexico, specifically in the Yucatan Peninsula. So the Yucatan Peninsula is divided between 3 states, being Quintana Roo, Yucatan, and Campeche. Yucatan would be the state where we were conducting most of our research, due that it has the highest Mayan population of the 3. We conducted a whole analysis of overlaying different maps, but the most important one would probably be the flood zones and high-risk zones. With this, we started looking into the Mayan culture, specifically their architectural typologies. And so this typology begins in the Mayan plot, or the solar. The solar has different functions, which are all arranged around the solar and are all correlated around based on distances from one function to the other. These also all oriented face, the apsidal forms are all oriented facing the predominant wind directions, ensuring that when we start studying these plot through like a CFD analysis here, we can see how the location of different trees mitigates and diffuses wind flow, while the house's form allows for wind channels to happen, allowing for cross ventilation throughout the whole plot. With this, we started looking at a typical Mayan house. These houses are constructed primarily out of 3 materials, which is wood, water, clay, or stone, and they have a great canopy system, which throughout the years have been losing the main natural materials needed to construct it, so it's being replaced by more concrete materials. Inside, it's an open space plan with an emphasis done towards the hammock, as the hammock rules this whole space. The design follows this. It follows a 2-to-1 ratio with a timber structure, with a main timber structure being attached to a secondary timber structure, where the roof and canopy is attached to using bejuco of natural fibers and knots. So we can see through a CFD how this system works great for cross-ventilation and for cooling down this house in this extremely hot climate, but although in storm conditions, it can produce an uplift force which will blow off the roof, resulting in high damages during storms. Here we can see how the house could be damaged throughout a different category of hurricanes, finishing with a category 5 that normally knocks out the complete structure. After this happens, the government obviously takes some action to help these people, and normally what they do is they provide the basic building materials to build a concrete block fondem house, as they call them. These houses, although hurricane resistant due to this concrete material, lack all of the thermal regulation or local materials that make the traditional house so good. Therefore, normally after the storm, when they have time, via community construction sequence, they end up rebuilding their houses right next to the block house given to them by the government.
So based on this, we started working at a multi-scalar approach, where we work in 5 different scales that go from landscape, material, morphology, microurbanism, and network. So let's take a look for the first 2 scales, which are material and morphology. For the morphology, on the MSc stage, we ran a first evolutionary algorithm to create a general morphology. And from there, a large deformation analysis was conducted to extract and select the stress lines, which were then rationalized, and lastly, a sequential evolutionary algorithm was run to define the structure, ending up with this result. However, we were having a missing link between the first and the second evolutionary algorithm on the way we were extracting the stress lines. So we decided to take a few steps back and study an alternative solution in the way we were getting the structure. So we extracted the mesh from the first evolutionary algorithm, and from there we applied the loads of gravity and wind in a category 5 scenario. And then we started looking at a shell analysis, looking into the maximum areas of compression and tension forces, and studying it into the inner and the outer layer of the mesh, reducing the mesh to only have the maximum areas of compression and tension, and then extracting the principal stress lines in direction 1 and direction 2. Overlay that with the maximum areas that we were having with the maximum tension and compression forces, and selecting by proximity these lines, by measuring the lines with the mesh we were having, and dispatch them accordingly in the direction 1 and direction 2. Furthermore, we overlap them again and do a second dispatch by the length of the lines, and a last dispatch by the closeness of the lines, ending up with these two sets of lines in the inner and outer layer, which when they overlay them again, and by construction criteria, we started selecting the ones that were not overlapping each other, overlay them again with the areas of maximum tension and compression forces, and finally we had to add a few more lines in order to keep the morphology we were working with. Then we rationalized these lines in the elastica domain of the bamboo to have this finite skeleton, which would then further run a finite element analysis in order to test this structure in a worst case scenario, again, a category 5. This is the displacement we are having with the sections of a 22 centimeter diameter. We're having a displacement of less than 40 centimeters in a worst case scenario. Bamboo has the tensile strength of steel, allowing for elastic deformations. So for the digital experiments, we created a material with the real values of the mechanical properties of the bamboo in order to have more accurate results. On the MSc stage, the main structure was proposed as a heat-bended single bamboos. However, the change on the design of the structure made us rethink the construction process. Bundling showed to be a better construction method for this complex geometry since it allows for redundancy and it's easier to bend. So we started looking into the best pattern for this bundling that we were working with. So we decided to make an evolutionary algorithm, which was optimizing for 3 fitness criteria, which was minimizing the displacement, maximizing the number of poles, and minimizing the mass. Here are some of the Pareto front solutions. And then we started analyzing individually for each one of the criteria, where we were seeing that if it was performing good for one, it wasn't performing that well for the other one. So we decided to go for one individual that was performing good for all of the 3 fitness criteria proposed, and compare that to the solution we had before of a single pole. So we can see that the bundling, we are having less displacement and it's a lighter structure as well. We then compared this and run a physical test in order to have the comparison between the physical and the digital model, where we can see that for a load of 27 kilos, we are having a similar displacement for both, that is less than 4 centimeters. Then we tried to optimize the amount of material we were using in this skeleton, so we mapped again the areas of maximum compression and maximum tension forces in the skeleton, and defined different zones for 2 types of bundling, which is a big bundle and a small bundle accordingly, which are gonna be connected with a simple overlap of each other and tie them together. We then started looking into the assembly sequence of this new structure, where the bundling will take place at the bamboo workshop and assembled directly on site, starting with the main rib and the central ring, which will be temporarily supported by shores, and afterwards the intersection and the rest of the beams will be measured and marked in order to attach the beams to each intersection. Once the structural stability is achieved, the shores are removed and the rest of the structure is put in place.
During the MSc stages, we designed a joint to actually connect this structure to the foundation we were having, and clearly with the changes in the structural system we were having, we needed to redesign this joint. So we did some changes to the node, moving from a fixed joint to an articulated joint, which will allow for easier construction methods. And also during the MSc stage, we were also looking at different material composites. So we're looking at different palms and fiber and different palms and latex or rubber composites, trying to create a new material that could create the same properties that the palms was having, but at a cheaper, more affordable price. We chose Enequén as our fiber due to its historical history in the region, as well as its clear availability and its usage throughout the years, as well as its great properties. So with this and some research, we were able to develop 4 different material composites, each with differential proportions of latex, fibers, and thickener. These were all measured in different ways in order for us to be able to digitally recreate this material, so we can continue to measure other things that we couldn't physically measure them as their translucent properties. The materials were then tested physically for elastic behavior as well as for air loads being pushed, and these were all compared and divided between the 4 different composites, which allowed us to start choosing in which areas of the structure each composite was going to be added, depending on translucent properties as well as ventilation properties we were seeking.
From there, we started dividing the skin into 2 different parts of panels, which are the breathable panels and the solid panels, and started designing a substructure which makes sense with the structure we were having and the skin we were developing. So we decided to have a quad panels. And in the breathable skin, we started making a clustering with 5 different parameters, which are perimeter, area, length, and the angle of the segments, and the position, ending up with 6 different types of panels, which would then further rationalize them in order to have an average panel for each one and have a single mold.
In order to design this mold, we went back to what we were learning from our material experiments, and we're noticing that the way we were creating these composites was ending with 2 distinct finishes. Finish A was a very smooth and water-resistant texture, while finish B provided a lot of friction when overlapped within each other. Therefore, we decided to design a mold that could allow for an edge of this very frictionless finish while having the center be a smooth finish. This would allow for the overlapping of the panels and allow them to move less during a storm. With this, we started looking at how these overlap would allow for ventilation, and especially how it will attach to the main structure. So through a very simple system of a screw top, a panel scaling, and then a bottom, this is all managed to attach to the main structure.
We then test this through a CFD analysis in 2 different scenarios. The first scenario, which is a day-to-day scenario, where we can see that the overlapping allows for cross-ventilation, and the second one, which is in a worst-case scenario, in a hurricane, where the breathable panels are removed and the static pressure is less. Then we have a top view of the dwelling with an open floor plan, as well as an elevation and a section, and an inside view where we can see that the overlapping allows for ventilation and the translucent properties of the panels.
We then started working at the 3 remaining scales. We started looking at landscape, microurban, and finally a network. As a recap of what we had done in MSc we created a flora catalog. These species of plants each had properties which made them great for storm resistant, as well as economic and cultural properties which would make it easier for the people to grow these plants. We then tested these plants, different arrangements, and how their porosity levels could help mitigate wind forces and protect different elements from the storms. With these conclusions in mind, we started looking back at the Solar and went back into this radial organization, adding 3 distinct rings of protection to be filled with landscape around the plot. With this, we created a multi-objective optimization algorithm where it could optimize based on different criteria based on the plot. To develop this, we came up with 3 distinct communal typologies. So we'll start with Chanimbao, which is a coastal town located to the north of the state. This town's main economic gain is from fishing. And so we can see the individual plots reflecting that, with a landscape producing mostly of cacti and palms, and then of a very small rectangular plot with a lot of emphasis on the closeness to the sea. So, as we said, an evolutionary algorithm was created to create a variation of different types of plots. These were each analyzed on their specific properties. So we could see for fitness criteria 1 distances, the best ranking one has the trees away from the houses, allowing for less damage during the storms. Or when we're looking at solar optimization, where we want more solar shading on these functions, they're clearly all covered with a small jungle of palms. Afterwards, we began working on a typology on an urban level. We began by creating agent-based simulations based on the predominant wind factors as well as around the milpas to work as agent spawn points. These agents' trails were then recorded into a mesh, which allowed us to then create a terrain based on different typologies. Before we moved on, we tested this terrain to see if it was working in wind, rain, and flooding conditions. And when satisfied, we began a sequential simulation of an urban layout, where the first simulation was run in the individual plots, and then we had the urban layout of the town optimizing for our basic criteria. We were looking for more bamboo for construction, more agave to provide fibers for biocomposites, and a bigger and better protected safe area from the storm. We can see the Pareto front solutions here, so showing some real morphological differences. And when analyzing the best and worst categories, we can see here for bamboo that we have a very marked perimeter around the individual plots, providing great protection. The agave is the opposite of this, and in the safe area, we can see a big, well-protected central milpa. We then started looking at another typical typology of the Yucatan. We started looking at the town of Chabab. Chabab is located to the South Hilly region, and it's a town that focuses mostly on agriculture. So its plot obviously reflects this. We see the inclusion of a small family milpa to produce some food for themselves and other to sell. And so based on this, a new fitness objective was added, where we wanted the biggest and better milpa area. And well, after running GA, we limited the Pareto front solutions and then began working into the topography, where we followed the same process that we followed before, having an agent-based system in order to create a mesh. This topological mesh was then analyzed through CFD, rain simulations, and flooding simulations, and once we were satisfied with the results, it was run through a sequential simulation again. Lastly, we started looking at another type of typology located in the central parts of the state, which is Alaba. Alaba is a town which most of its economic gain comes from animal husbandry, so animals take a specific importance here in the plot. So when we're looking at the plot, it's quite similar to the last plot, also having a milpa, but with bigger areas for animals. We, again, went through this whole system, optimizing this plot based on most area, the best distances, and the best solar gains, and the Pareto front solutions were recorded and then limited in order for the sequential simulation. Again, we ran an agent-based system, this time based around the plot and where the predominant wind direction was coming. The trails were outputted into the mesh, and then this mesh was tested through the same processes, ensuring it was working before being run through a sequential simulation again, optimizing for a highest bamboo area, the most agave or materials, and the best safe zone possible. Afterwards, we started looking at the evacuation network. Currently, the evacuation network in place is run by the government, the municipalities, and it's very limited per se. It's mostly focusing on the northern communities of the state, which face storm surge risks, and the distances that they need to travel are quite long, so we started to rethink this. We began by selecting all of the Mayan settlements in the state and then just limiting them to the state of the Yucatan. Then we limited those to the communities that weren't close enough to an already located urban area where they could evacuate to. And then through a process of k-means clustering, we developed 20 different clusters responding to each of the municipals in the state so they could organize the evacuation. Afterwards, these new safe points were identified, and a multi-objective optimization was done in order to locate the best location for these safe zones, optimizing for the maximum settlements in reach of each safe zone, the minimum travel distance to the safe zone, is the most communities connected within this network, and finally having the least amount of safe zones located within the network.
And to wrap everything up, we started looking into the life cycle of the whole project at the different scales. And we started naming the different activities you have to do throughout the whole life cycle of the project, which is planting, harvesting, treating, prefabrication, storage, construction, evacuation, and finally reconstruction. And starting to see how the different scales relate to each one of these activities. And to sum up, that we have a completely integrated, resilient program for the Mayans during a hurricane.
Well, thank you.
Thank you.
Is this on? Yeah? Hello? Yeah, okay. I think it's a fascinating project, and I think it's got a level of resolution to it which, it's very rich. And so, I congratulate you on that. Some of the imagery like this one, they're spectacular. What I would say is I'd like to understand a bit more, and I think I might have asked you this before, who is building this? And, if you think about the current vernacular, what you've got there, they're fairly rudimentary. They're through well-established construction processes that they understand and they're well versed in. And I appreciate that as part of your construction process that you've put in place. You talk about the panels, you've made them as repeatable as possible. So that's fairly good. But you've got these crazy, beautiful, but also crazy complex kind of bamboo structures that somehow need to be set out on site. Now I can imagine, if that was to be built in the UK, there'd be, 1,000 laser scans, there'd be, points everywhere, people would be doing GPS all over the place just to try and get it in the right place. How is that going to be done en masse? And so I'd like to understand that a little bit more. Maybe a solution is prefab, maybe it's, and I'm not saying prefab components, but prefab jigs and things like that. But I think there's a big kind of leap of understanding that feels like that it's missing there a little bit. There's a lot of, very well executed part of this. You've touched on a lot of the questions that I had coming up in my head. The next slide, you touch on it, which is what, we want to see from a presentation. But I think that there's a bit there in terms of, thinking about that user. And to be honest, it's a bit of a theme running through all the projects today, is actually the user, the people who are going to be building this. And I think that really needs to be touched on a bit more. These beautiful objects, these beautiful sculptures that are being created, who is going to create them? And I think you really need to kind of put some thought into that. I'm sure I've got other questions not coming to mind at the moment, but I'll pass on.
Thank you very much for your presentation. It's really an outstanding project. I think the richness of the analysis and the way that you are very thorough and almost engineered everything. It's really again I find it very fascinating. I'm not going to dwell with what Andy had. I had the same comment, but I think I want to talk about a little bit more about how this kind of morphology, as you call it, I'm going to simplify this word, this shape that you came up with, has maybe a different resolution if you are close to the coastal area or you are more in the inside. The reason why I'm asking is that you have quite different problems. If you're really close to the coast, one of the issues is water, getting at the ground floor. So I would have expected your shell to somehow embed a system where, the ground floor is not on the ground, but is elevated so that you're still going to be completely flooded. Maybe you resist to the hurricane 5, but yet not everything that you own will be completely in the water. So especially when it comes maybe to the animals. And it's the same, I mean, you decided to do, and it's very in-depth. I mean, you decided to do the one on the coast, the one where animals are the most important thing to save, apart from humans, of course, but that they are really in the middle, and maybe there, it would have been nice to see yet another organization of these, because I remember from a previous presentation you were saying that during a hurricane, humans and animals, they all fit inside and they save themselves by just being together till the storm is past. But I think if you have 2 chickens and a dog, it's easier. But if you have 3 cows and 5 sheep and 3 dogs, maybe not all together in the ark. So I think there was maybe, and I understand the time and constraints and so on, but there is a level of where this fantastic study could have given us a glimpse of adaptation into different, requisites or different environmental conditions that could have, give us a hint of how this drawing or shape could have been modified accordingly. But nevertheless, very nice presentation. Thanks.
Thank you.
Yeah, I agree. I'm working on a hurricane-prone bamboo tower in Bali. We dropped the bamboo, and the reason is it's very hard to quote unquote warranty it for years of exposure to the rain, to the wind, it has a tendency to be very brittle, and so you end up dipping it in plastic, epoxy, and it just becomes a cry, and then we just dropped it and went for ironwood. I know there is a chipotle or woods like this because we're doing one in Bacalar as well now. So we switched to hardwoods, reclaimed hardwoods, which don't need to be treated because they're naturally resistant to insects and so on. I'd be very curious to see a life cycle assessment if you dip this in plastic or in your biomaterials that you seem to have collected, which is really interesting. Would this still be better than concrete? I am also curious about the human making. It feels, although it's a beautiful image, everything is clashing with everything. The lashing is sort of entering the bamboo itself. And I say this because I know it's complex to model, and you spend a lot of time on bundling, but not necessarily on the lashing itself. It's really hard to do lashing. And if you have such radius of bending to put so much pressure on the lashing, I just wonder if you should explore straight segments. Because this segmented, the curvature is so small because you are. I mean, when you take each one of those segments as they intersect, if you use straight segment and you lash these straight segment, you might have the same behavior, make it much simpler for people to build it. I think the idea that they can make it is really important, but that is not tested. Look, I'm not seeing a time frame of people assembling stuff on site, and I think that will be the main aspect of the vernacular you were showing that was really nice, is people can build it. Whereas the concrete one, I don't know, it's, or you showed a metal node, it might be a little bit harder to do it with that, but this is a really important aspect. I think, yeah, sorry. And so I was just wondering also about you showed a single story one. I was kind of expected to see it grow slowly into a multi-story building. I'm very curious about your approach and see how it can scale up into maybe something that's a tiny bit more like a tiny bit different for a different topology, or yeah. But yeah, I really like this image.
We also, the concrete foundation node that you were mentioning, we have that prototyped upstairs, but it was a bit heavy to bring down. It's a 2-meter concrete block with a bamboos attached to it. We also, we generated the biocomposites and the skins, and also modeled the bundling system. Yeah.
All of the thing that you say about the tying, and it was
chaotic.
Yeah, very time consuming and quite chaotic. Yeah.
It's very hard. Yeah.
It's just sort of nodes and knots and
Yes.
I'm very curious about it. That's why I'm asking all these things.
I mean, the idea is to have it everything throughout traditional methods. So it would be bending traditional methods and curing traditional methods. It wouldn't be like synthetic curing for the bamboo. So it would be like soaking it into water or heat bending or putting it to mud to extract the sugar. To extract the sugars, and and then it will be protected from the insects, and it will have a lifespan of maybe 30 years or more.
Yeah, that's what I was going to say, that through the process of heat treating it, you're actually melting down the cellulose in the bamboo surface. And so when it is drying and it like re-hardens, the cellular structure changes, which then coats like naturally the bamboo in like a natural wax of its own cellulose burning, like just the outside of the bamboo. So we did consider those types of issues. That is done before the heating. Yeah, before the lashing. Because it's when you're heating it, you can also start to modify the geometry of the bamboo, and then the spring back is much less, so it would allow for easier creation of these complex bundles where you can treat the bamboo individually, heat bending it, and then start giving it some of the basic geometry. So when you actually build this, the spring back isn't having that much of effect on the lashing that we were creating.
I'd be very excited for you to go in Bali or there and then to just actually build it. Yeah, sorry.
That's the plan.
Please do that.
We're going to find funding, so.
Yeah, put this on Kickstarter. I give you some money. Honestly, it's really interesting for everyone. It's good research.
Thank you.
I'm fascinated by the lashing because the maritime tradition is quite different. The American Indians and the North American Indians used cattle hide. Pig hide would do as well. There may be an ethical point that you don't want to address with that.
Okay.
But the property of that is that as it dries, it shrinks.
Okay.
And it becomes iron hard. So it was a traditional North American and South American Indian technique for using different section timbers that didn't fit very well, that as you lash them with an animal hide that's wet or raw and allow it to settle, it will dry, it will shrink and become incredibly tight and hard. You can't even cut it with a knife. And, so if you could combine that with your natural waxing, I think you then have a very interesting, highly viable potential system. I'd love to see you build it.
So would I.
Cool.
Thank you.
Thank you.
Yes, thank you everyone, and we'll continue in the evening at 6:30 with Andy Watt's lecture, so please join us. And thanks to all of our students for all the hard work.